Hi everyone, this is Mike Eblowitz from SoftSteel. Today I'm going to show you our flagship product, SoftSteel, the 3D automated steel detailing system. There are modeling systems that detail, and then there's detailing systems that model. Our system is a detailing system that models. What that means is that detailing is the #1 priority, and that being the quality of the output of the shop drawings. The shop drawings are not just an afterthought, as they are in most 3D modeling systems. Our shop drawings are our main focus. When you first fire up SoftSteel, which by the way runs in any version of AutoCAD from 2000 through 2015, 32 or 64-bit, it brings up our project wizard. In the project wizard, it'll list all the projects that are currently on your machine. Or you can select a new project. We'll put in a new project called Core 2. And that will open up the system. Across the top of the screen are the toolbars that are related to SoftSteel. You can place your toolbars anywhere you want on the screen. Each toolbar, of course, when you highlight it, will give you a quick description telling you what it does. The first thing we're going to do is fill out the project properties, which is basically your title block. So we'll go ahead and fill out the project as being my new office. And the address will be 123 Main Street, Los Angeles, California. And the architect can be Smith, and the engineer can be Jones, and the customer can be ABC Construction. And the job number is Core 2. The job number you're filling out here is the job number that actually appears on the drawings and the reports. It doesn't have to necessarily be the same as the job number that we use to call up the job in the system. Okay. The company name we'll say is Core Dynamics. And the address is P.O. Box 5352, Dubai. And it'll be drawn by Mike, and it'll be checked by no one. Okay, and for paint we could say one shop code or none or whatever's appropriate. Okay, the default grades are going to be A992, which means if you don't specify a grade, that's the grade it's going to default to. If you're using European or British shapes, you would choose grades that are relative to those shapes. The version of the system that you're looking at now is the version for sale in the United States. So it's got American shapes and American grades. And we're going to do everything in imperial. But you can also do your input in metric, and you can do your output in imperial or metric, or any combination of the two. Okay, when you do an input in our system, north is always straight up on the sheet. This is where you get to tell it where true north is or project north is in reality. And it'll make the conversion for the column drawings and the erection drawings. You can then take this and save it as a template. And then the next time you start a new project for this particular fabricator, you can select it, load it, and everything will be filled out, and you can just modify what you need to change for the new project. When you've done something worth saving, click this icon here for Save Job. And the project is now saved. If your machine crashes or the power goes out, you cannot get hurt as long as you save your project as often as possible. Okay, the next icon is basically setting different switches for setting up your environment. For example, we're going to do everything in reference mode, which means everything is relative to grid lines. This is different snapping offsets. When we show material on the screen, we're going to show the elevation, the mark, the description, and something called the tag, which I'll get to in a few minutes. We're also going to show everything as a line, which means we're going to do this as a wireframe. If you uncheck it, then it'll show the full 3D profile. When you're inputting a job, it's usually better to do everything as a simple wireframe, because then it's simpler on the screen, it's less work for AutoCAD, and it looks just like the design drawings. Okay, and for connections, we'll say show the visual connections. Okay, let's save what we've done. Okay, we have online help built in the program. If you click that icon, it takes you to the top of the help. Or if any particular screen you're on, if you press the F1 key, it's context-sensitive help. It takes you right to the help for that particular dialogue that you're working on. Okay, we're going to start off by putting in some grid lines. We have three different kinds of grids. North grids run north and south on the page. East grids run east and west on the page. And H grids are your horizontal grids, or your top of steel elevations. And you have three different modes: relative to what you did last, relative to something that you choose, or absolute from the origin. We'll start with relative to last, and we're going to do a grid line 1 at 0. Grid line 2 is 20 foot relative to grid line 1. Grid line 3 is going to be 20 foot to what I did last, 4 and 5. Now I'm going to go east grid. A is at 0. B is at 20 foot. C, D, and E. Now we'll do H grid. Now we're going to go absolute, and we'll create one called FF for finished floor, and it'll be at 0. And we'll create one called second, and we'll make that 12 foot 6. And we'll create one called third, and it'll be a 25 foot 6. And then we'll have one at the roof. The roof is going to slope, so what I'm going to do is choose an arbitrary point. I'm going to choose the ridge, or the high point, at 39 feet. Then the last thing I'm going to do is create one for the bottom of my base plates. I'm going to call it BOP, and I'm going to say relative to FF minus 10.5. And the reason I'm doing this is because my footings are 1 foot below the slab, and I have 1.5 inches of grout or dry pack. So therefore the bottom of my base plates are at minus 10.5. The reason I'm making an H grid for it is so that when I put in 500 columns, I don't have to constantly say FF minus 10.5. I can just say BOP. Later on, if the engineer changes the grout from 1.5 to 2, or drops the footing down to 1 foot 6 below the finished floor, all I have to do is change BOP, and everything that's referenced to that grid changes automatically. It's kind of like a domino effect, and it's very, very powerful. Okay, so there's our Cartesian coordinate system set up. Now I'm going to go to this thing called the Navigator, and this allows me to walk around the model. If I hit and right up here and down here, it shows you where you're at in the model. So right now I'm at BOP, and this is a 3D view, but I'm looking straight down. So this is a plan view. I'm looking at FF, second, third, roof, back to BOP. Hit the round arrow key. Now I'm looking at an elevation view of grid line 1, 2, 3, 4, back to 5, back to 1. The down arrow takes you the other way. Hit the round arrow. Now I'm looking at 90 degrees to that, looking at an elevation of A, B, C, D, back to A. Okay, if I hit the southwest isometric icon, I'm now looking at southwest ISO view of the BOP level. If I hit the solid square icon, it looks at all levels. And then, of course, you can rotate this around on the screen using AutoCAD. Okay, but I'm an old-time detailer, so I like to work in plan view and elevation view. I'm going to go up to the roof. And I told you that the roof's going to slope. For the purposes of the demo, we're just going to do a simple slope going at 1/4 and 12 bevel down to the left and to the right. In other words, the high point or the ridge will be at grid line C in the center of the building. Now what I'm going to do is use a tool that's unique to our system. It's called planes and lines. Planes are for smooth surfaces and lines are for warped surfaces. So I'm going to choose planes, new plane, and I'm going to give it a name. It's suggesting the name PL1. You can call it Mike or anything else you want. And I'm going to choose 3 points. Okay, the first point is 3A at the roof, which is 39 feet. The second point is 3D at the roof, which is 39 feet. And the third point is going to be 1B roof minus 10, or I could say, I can hit this box right here and it gives me a drop-down list of all my H grids. FF plus 38 foot 2, which is what I'm going to do because the 38 foot 2 dimension was given to me by the engineer on the design drawings. That way I don't have to do any math, which eliminates the possibility of a mistake. Now I'm going to create another new plane called PL2, and I'm going to choose 3 points. 3A at the roof, 3D at the roof, and 5B, and we'll say FF, and I'm going to say 28 foot 2, which is an obvious mistake. Now I'm going to go to the navigator, switch views to a side view of grid line A, and I can see that this plane is obviously not correct. And if there's a bunch of steel tied to it, that steel would be incorrect as well. So what I'm going to do is select Modified Planes. Basically, you look for the same icon with a wrench on it. The wrench means we're going to fix it. Select it, and I can see there's my mistake. So I'm going to click Apply. That's going to relocate the plane, and everything that's referenced to the plane, all the beams, columns, channels, girts, braces, struts, whatever's referenced to that plane would automatically adjust with the plane if it was referenced to the plane when it was input. Let's go back to a plan view of BOP, and let's save what we've done. And I'm going to put in a couple more grid lines. Let's put in a north grid relative to grid line 2, and we'll call it 2.3, and we'll say it's 3 feet. And let's put in a grid line 3.7 relative to grid line 4, and it's going to be minus 3 feet. Okay, and I obviously made another mistake. So what I'm going to do is go to Modify Grid Line, and select 3.7, and it should be relative to grid line 4, and it should be minus 3 feet. And that puts it in the correct place. If you want to move a bunch of grid lines, let's say the engineer changes this dimension from 17 foot to 18 foot, you would just go Modify Grid, select all these grids, and move them 1 foot 0 relative to themselves, or minus 1 foot if you want to go the other way, and they'll all move the same amount relative to their current location. Okay, let's save what we've done. Okay, now let's input some steel. Let's start off with column input. And let's put in a W14 by 370. And we can choose a point here. So it's putting it in at 1A BLP, which is perfect. That's right there. And for the top of the column, if I don't want to navigate to the top of the building, I can do the drop-down list and choose plane 1. So what it's going to do is it's going to take the intersection of grid line 1 and grid line A, create a vertical line pointing straight up, and when it intersects plane 1, it's going to know the elevation, which happens to be 38 foot 2. The direction is south versus east, and you can rotate it degrees of rotation. So if I click Add, it's going to add 1 column. I can now delete that column by using AutoCAD. Right-click Erase. By the way, you can use any AutoCAD command on SoftSteel objects. So the more you know about AutoCAD, the more dangerous you can be. Okay, I'm going to go back. The dialog's all filled out, and I'm going to click Spacings, and I'm going to say give me 5 of them, going from here to here, and give me 2 of them, going from here to here. And I did this one wrong. It's from here to here. And now when I click Add, it's going to give me 10 columns. These might be 10 different shipping marks when it's detailed. It doesn't matter to us. We're just building a model at this point. The system's going to automatically, with one click of the mouse, create all the shop drawings. It'll figure out combinations, how to present the drawings. Everything's automatic based on settings that we set up front. Now if I climb up to the roof, I can see that my first columns are 38.2, 38.7, 39 foot, then 39.5 and 39.10. So I made another mistake. These four columns are on the right half of the building, and this plane slopes down, so they're going through the deck right now. So I'm going to look for a piece of steel with a wrench on it, which means I want to fix it. And I'm going to rubber band those four columns. And I'm going to say change plane 1 to plane 2. Or I can do the drop-down list, or I can change it manually. Now, you can see it goes from 38.7 to 38.2. Let's see what we've done. Okay, let's go to the navigator and go back to BLP. Okay, let's input some more columns. Now, one thing that I wanted to do is introduce tags. Tags are unique to our system. They use definable labels. With a tag, you can do things in a global fashion. You can create a tag or a label, apply it to steel, and then tell it by the tag's name to do different things to the steel. For example, if you have a room full of people and half of them are the name Mike, you could say everybody named Mike go to the left side of the room. With tags, you can create a tag called M for moment. And you can tag your moment steel as M and then write a moment connection and say this applies to all steel that is tagged moment. So I'm going to create a tag called BP1. I'm going to give a description. And I'm going to copy this to the Windows clipboard so I don't have to type it again. And I'm going to add that tag, base plate type 1. Now I'm going to create a tag called BP2. And one more called BP3. When I create these tags, I'm going to put them on the columns, and then I can apply different base plates to different columns based on the tag, which is how an engineer typically does it on his design drawings. He'll show a schedule, and he'll show 3 different kinds of base plates in the schedule and say this is base plate type 1, base plate type 2, and base plate type 3. Now the engineer is not calling it tagging or tags, but it's the same thing. He's setting up 3 or 4 different types of base plates. So we're going to create 3 or 4 tags to represent those base plates, and then we can apply them globally. Okay, now I'm going to create another tag called M for moment. Now I'm going to create one called GLV, and the description is going to be galvanized. And I'm going to say plot it on the bill and plot it on the sketch. So whenever a piece of steel is tagged GLV, it's going to plot in the remarks field of the bill of material and on the sketch itself. In addition, I'm going to give it a priority of 1, which means detail it at the beginning of the job. You'd want all your galvanized material up front because you need the lead time to send it out to the galvanizer. I'm also going to create one called HLD. And I'm going to say plot it on the bill, plot it on the sketch, and give it a priority of 2. And that one, the description is going to be hold. This is for stuff that we have RFIs out on. There's no limit as to how many tags you can add, and you could save it as a template. So we could save it under the name Core 2. Then when I start a new job, I can load up the template for these tags, and I don't have to do it all over again. Let's save what we've done. Okay, let's put in some more columns. First, let's go to Modify Material, rubber band all 10 of these columns, and we're going to add the tag BP1. You can have up to 6 tags on any piece of steel. I've used as many as 5 on some jobs, Typically it's just 1 or 2 tags you're going to add. And if you zoom in, you can see that the tag was added to these 10 columns. Later on, I'm going to write a base plate, and I'm going to say this particular base plate with these parameters apply to all columns that are tagged BP1. Okay, let's put in another column. This time, instead of W14 by 370, we'll say 12 by 96. And we're going to tow it east instead of south. And we're going to give it the tag BP2. And this time, instead of using these buttons to pop the steel into the model, I'm going to click the multi button. And I'm going to say the bottom is at BOP, the top's at plane 1. And now I'm just going to start clicking away. There, 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 there. Now I'm going to come down here and say change the top from plane 1 to plane 2. And there, 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 there. Hit escape. And now I'm going to put in some HSS 8 by 8 by half. And the tag's going to change from base plate type 2 to base plate type 3. And the grade's going to change to A500. Multi. There and there. Escape. Okay. Save what we've done. And let's zoom in and see what we have. 12 by 96s, BP2. Okay, so that all looks good. Okay, now let's climb up to the second floor. And let's put in our beams. Let's put in a W24 by 76. And the tag, instead of BP3, is going to be M for moment. And the grade's A992, and I can choose a point here and a point here. Okay, and I can go spacings, and I can say give me 2 of them at 20 foot in the east and 2 at 60 feet in the north. I'm only going to put in the left half of the building, and then what I'll do is I will mirror it to show you that capability. So I'm going to go ahead and click Add. And there you can see the 2476s. Okay, now I'm going to take it and change it to a 2462. And instead of moment on both ends, I'm going to right click it and make it moment only on the mark end, which puts a 1 in front of it. Sorry. The left end's at 1A, and the right end is right here. And I'm not going to have any multiples, and we'll click Add. And now we're going to make moment on the other end. And we'll go from 1C to 1D. You can just come in here and type it if that's quicker. Okay, now we're going to have no tagging. And let's put in a W18 by 40. And it'll go from here to here. And let's give it a half-inch camber. You see the camber on it. Okay, let's take the camber back off. Now I'm going to put in W16 by 31s. And this time I'm going to use the pick button. And now you can just start picking away, just like we did with the columns with the multi button. If you make a mistake, just keep going. You can come back and fix it later. If you put in a piece of steel backwards, the system will automatically rotate it into the correct position for you. You can never put steel in backwards. Okay, when you're done, hit Escape or Enter. And we did something worth saving, so I'm going to save the project. Okay, now what I'm going to do is create some work lines. so that I have something to snap to. And I'm going to go from here to here, here to here. I'll go the other way. And then we'll also put one in at 10 foot. Going from here to here. Okay, now let's put in some steel. Let's go W14 by 22. And I'm going to use the pick command. And now I can use those reference lines I just put in to snap to them. Hit escape when I'm done. Okay, let's save it. Okay, and now I want to mirror this to the right side of the building. So I'm going to click this icon here that says Mirror Member, and it's asking me to select my objects, but I have a little problem here. I only want to select my beams, my braces, my channels, my girts. I don't want to select my columns because I put in the columns for the entire building. In hindsight, I should have just put in the left half. So what I'm going to do is click this button that says Filter Members, and I'm going to say Select Columns and hide them. Apply. The columns are still in the model, they're just hidden from the screen. So now I can do Mirror Member, rubber band everything in the left half of the building, create a mirror line going from here to here, delete the source objects, no, and we have a true mirror image to the other side of the building. I know you could do mirroring with AutoCAD, but AutoCAD's not structurally steel intelligent. In other words, if you had a channel right here, it would have to toe the other way. AutoCAD would not know that because it doesn't understand what steel is. SoftSteel is structurally steel intelligent, so it would know to do that. So we prefer you use the SoftSteel icons simply because they're more intelligent when it comes to steel. Now I'm going to project this up to the third floor. I'm going to use the project command, and I'm going to rubber band everything on the second floor. And we're going to project up, delete the source objects, no, and we're going to project it to the third floor. Go back to our filter button, show our columns, and let's save what we've done. Okay, so if we go to the navigator, you can see the second floor and third floor are in and nothing's in on the roof. So let's put some steel in the roof. Let's put in a W24 by 76 again. I know this is a simple building, but it's a demo, and we're trying to get the basic capability across to you. Let's put in a beam going from here to here. And it's going to be plane 1. And spacings. It remembers what we did before. So if you look at the steel now, you can see it's going from 38.2 to 38.7 to 39 feet. So now I'll make that a 24 by 62. And let's make a moment all the way across, and we'll go from 1A to 1B, and we'll say nothing in the east, and we'll say 3 of them at 20 feet this way. Okay, and now let's put in some 16/26s, and we'll have no tag on it at all, and we'll go from here to here, and that's plane 1, and it'll be 2 at 20 feet, and then it'll be 2.3 to 3. I'm doing it this way to show you that you don't always have to do things graphically. Sometimes it's quicker just to select or to type, depending on what you're doing at the time. Okay, and now let's put in a beam going from here to here. And that's plane 1. And there's no spacing, so we'll hide it. And I'll go from here to here. And then finally from here to here. Notice when it's in red, it's syntactically wrong. There is no grid line called RPO1. As soon as you type something that's correct, it'll change colors back to black. Okay, and then we're going to go from here to here. And that's plane 1 and plane 1. And 3 at 20 feet in the north. Okay, save what we've done. Okay, let's go back to our filter and let's hide the columns again. Let's go to mirror member and let's mirror all the beams on the roof. And the mirror line is going to be here and here. Delete the source objects, no. And you can see that it's going from 39 foot, and it recognized the fact that it's got to slope the other way. So let's go back to filter members and show our columns again. Okay, we put in enough steel for right now. Let's go and write some connections. To do that, I'm going to click the connection icon, click new. And by the way, everything you're about to see now with the connections, you get a manual for it. I believe in hard-covered books or loose-leaf binded books, and basically all the connections are in paperback form as well as digitally on the screen. So that way you can plan and your connections out before you actually even turn on the system. Okay, we're going to go to our connection browser, go to base plates, go to a connection called base plate type A. We're going to give it a friendly name. We'll call it BPA for tag BP1. You can call it anything you want. This is just meaningful to this job. Member 1 can be anything, and member 2 is going to be a column. I could say footing for member 1, but then I would have to put the footings in, and I don't want to be bothered. Okay, every connection has up to 30 parameters associated with the connection. So I can have 3 rows of bolts this way by 2 rows of bolts that way. And by the way, here on the bottom it shows you in text form what the parameter is, and over here on the screen it shows it to you graphically, and of course the book shows it to you as well. So the thickness of the base plate, let's make it 1.5 inches thick. Size of the fillet weld all around, I'll skip it. This is for my moment columns. Let's go with a 1-inch diameter anchor bolt. The plate dimension, I'm going to let the computer figure it out. It never gets it wrong. If the engineer gives you the dimensions, then of course you would use what the engineer gives you. Center of rows, we'll say 11 inches this way, and this way we'll say is 8 inches. Okay, we could say it's milled in. And for the welds, I'm going to say use a fillet weld to the web, make it 5/16, and to the flange, we'll go full pen. Oversize a hole, we'll say is 5/16, so the hole will be 5/16 larger than the anchor bolt for adjustability in the field. We'll go with the typical 1/2 inch minimum ledge, and then you can offset the holes left and right or up and down, and the plate will stretch automatically. The holes will never go off the plate. So there's our first base plate. So now I'm going to right-click copy, right-click paste, and this is going to be for my non-moment 12-inch columns, the ones I tagged BP2. So I'm going to come in here. Let's go back to connection BP1. For column, I forgot to say that it's for all columns that are tagged BP1. So this connection would only apply if the column's tagged BP1. And this connection would only apply if the column is tagged BP2. This time I'm going to do a 2x2 hole pattern with a 1-inch thick base plate. We'll do a 1/4-inch fillet weld all around. We'll go with a 3/4-inch diameter anchor bolt. And we'll go with a 7x7 hole pattern. Square cut. And we'll take this out. We don't need it anymore because we're going with fillet weld all the way around. And the oversize will be 3/16. Okay, copy, paste. And this is going to be for my HSS 8x8 column, which I tagged BP3, but just to show you something different, I'm not going to use a tag. This time I'm going to do it by size. I'm going to say this applies to all HSS 8. That's enough as it is. Or I could say 8x8. Or I could come in and say 8x8 by a half. I'll just say 8x8. And we'll do 2 rows by 1 row. We'll make the thickness of the plate 1/2 inch. 1/4 inch fillet all the way around. We'll go with a 1/2 inch anchor bolt. And we'll go with 11-inch spacing by 0. Square cut. And that's good. Okay, if I ran the job right now, what would happen is the only thing that would get detailed is the columns with base plates on it. And that's it because I haven't connected anything else. So now let's get into our shear connections. The system has a full complement of shear plate, bolted angles, welded angles, vertical tees, seated tees, any kind of end plates, any kind of connections you can imagine we have in the system. We have over 180 connections, each with its own parameters associated with it. I'm going to make this a shear plate job, and before I apply my shear plate connections, I'm going to show you something called connection schedules, which very closely emulates the schedules you see on design drawings. I'm going to create a schedule called CS1. Say this applies for W8s to W10s, 2 rows of bolts. The thickness of the plate is 1/4 inch. A325 N. Bolt diameter is 7/8, and the weld size is 3/16. Now I'm going to duplicate line, and I'm going to say W12 to W14. It's the same thing with 3 rows, but the plate goes to 3/8, and the weld goes to 1/4. Let's duplicate the line, and this is W16, 4 rows. W18 is 5 rows. W21 is 6 rows, but the plate's going to go to 1/2 inch. Let's make these bolts 3/4. And we'll keep the 21 at 7/8, and the weld size is going to go to 5/16. W24, I'm going to also keep it at 6 rows, but I'm going to center the hole pattern by saying the hole's down 4.5 inches. Now we don't have any beams that are bigger than 24 in this job, so I'm not going to fill out the rest of the schedule. Basically, you would fill out whatever the engineer shows you on the design drawings. You can have up to 7 different schedules for shear and 2 for bracing. So now I'm going to go ahead and apply my shear plate connections, and I'm going to start off with the simplest shear plate for my columns. Actually, it's going to be for my columns, and it could be for my beams as well. If I say member 2 is a beam and member 1 is anything, then this connection would apply a simple shear plate, beam to column, beam to beam, and beam to wall, embed connection. I'm going to tell it to pull everything off connection schedule 1, or I could actually fill out the rows of bolts, or I could say use uniform load, and it'll use the design formulas to figure out how many rows of bolts. Or I can go UL plus percentage all the way up to 100% end reaction. Okay, down here you can see in text form what the thicknesses are. Everything's going to come off the schedule, so I'm going to leave everything out. The only thing I'm going to override is I'm going to say for the clearance 3/4, and then for the edge distance on the beam 1.5 inches. Well, I can just leave it out. I'll just say the 3/4 inch clearance. There's variables for everything: grade of steel, horizontal, vertical edge distance. Anything you don't, short slots or holes, anything you don't fill out will revert back to a default or to the schedule. You can control the strike face. If you can't swing a beam in because it has wraparound pour stop, you can put the plate on the inside of the building. You can put opposite stiffener plates. You can put a cap plate. But this is a demo, so I'm not going to go crazy filling out everything. So right now, everything on the job is going to be a simple shear plate connection. So I'm going to get a little more specific. And if I'm going to choose a connection called SPI, this is where the plate is welded to the web of a column and it sticks outside the toe of the column for erectability. I'm going to give it a friendly name, SPI. Remember, one's a column. And member 2 is a beam. And the direction is web. So this only applies when the beam frames to the web of a column. And I'm going to tell it to use connection schedule 1, and in the interest of time I'm going to default everything else. Okay, new. Now I'm going to do a through plate connection. For my tube column. Remember, one's a column. And the size is HSS. So this only applies when the beam frames to an HSS column. And it shows you down here what you filled out. So this will not apply to any of my wide flange columns. You can see you're getting the feeling that everything we're doing is global. And that's by design. If it's global, it's quicker and there's less chance of making an error. I'm going to default everything else. The only thing I want to do is put a cap plate on it. I'll tell you what, we'll do some short slots too, just to do something a little different. Say 1/4 inch cap. Okay, and then let's write a beam-to-beam connection. SPB. This is where it's fitted on the top flange. Remember, one's a beam. And member 2 is a beam. Again, we're going to say connection schedule 1. We can do opposite stiffener plates and so on. Okay, now we need a moment connection. So this will be welded moment. Remember, one's a column. And member 2 is a beam. And when there's no direction, and when the member 2 beam is tagged moment, apply this connection. So we can say number of rows of bolts vertically. Again, connection schedule 1. Stiffener plates, yes or no. That's continuity plates. We'll say yes. Would it be a moment connection without it? Type of bolt, diameter of bolt, doubler plates. Let's say doubler plates on both sides. And let's go with a 1/2 inch doubler. And let's say the doublers go 3 inches above and below. And I want to get down to the welding. Okay, and we're going to go with a 5/16 fillet weld to the web. and full pen to the flange. And I want to put a cap plate on it instead of continuity plates at the top, because if you do continuity plates at the top, then you have to extend the column an inch higher so you can weld the top of the continuity plate. So I'll put a cap plate on it. I created some interesting situations here because I told the doublers to go 3 inches above and below, yet I have a cap plate on it. The system will be intelligent to that, and it'll know how to fix it. Unlike other systems, it will not be a clash, because a clash is what detailing is really all about. A system that automatically fixes it and puts out the shop drawings is a system that will be quicker and makes you the most amount of money. It may not be the most impressive thing to look at graphically, but we're not here to be impressed. We're here to produce results. And that's what our system is. It's a detailing system first. Okay, in the interest of time, I'm not going to write any more connections. I think we have enough. Let's save what we've done. Okay, now we can just process the job and see if it produced any errors. These are things that cannot be resolved automatically. The only error we have is in error code 5 in the WMA connection. So if we go to our help or to the manual, go to troubleshooting, error codes, and this is in alphabetical order, so we'll come down to WMA. Error code 5. The describes distance down to the first hole is less than the legal minimum. It's probably complaining about the plate hitting the rat hole. I'm going to let that slide for right now. It's just a demo. If you look at the model, you'll see that the names of the connections, let's go to a particular floor. It shows you the friendly names. Here's the SPA going to the flange, SPI going to the web. Here's the SPJ through plate connection going to the HSS columns. I did want to do a drag and drop connection, so let's do that. Let's go back to connections. And let's write a bolted framing angle connection. Double bolted framing angles. Call it BFA. And we'll say beam to beam. And again, we'll say connection schedule 1. And the only thing I'm going to override in the schedule is I'll make it a 5/16 angle. Everything else I'll default. Now this, I don't want this to be global. What I'm going to do is click this button here that says apply to supported member. And I'm going to select this beam. Let's go all the way across the building. This beam, and this beam. And we're going to do it on both ends. Replace the current connection. Okay, and it'll highlight in violet or purple, showing you that it was a drag and drop or a specific connection. And just to make things interesting, let's take these two beams and let's offset them. Just to show you what it does with the clip angles. Save what we've done. Okay, now that our model's built, we save it. It's always a good idea to exit the system and save it to a backup device. You never know if tomorrow morning your computer may not turn on. So what we're going to do now is with one click of the mouse, we're going to detail the whole job. Now one thing I did not show you in the demo so far is define standards, where you set up the marking system, what sheet numbers you want to start with, whether you want general notes on the drawings. Let's put some general notes on the shop drawings. It says no paint to 3 inches of holes unless noted. Okay, you can tell it to start with any sheet number you want. Then we can go to the, we can do 24 by 36 multiple sketches per sheet, or we can detail any of these other options, 11 by 17, one sketch per sheet. You can detail by erection sequence, which we call by pile. You can do upper lower case. Let's do lowercase, shoulder weld on both sides, and the column section piece marks. You can have a marking system like 1C1, 2C1, 3B1. I'm just going to do 1A, 2A. You can use standard angles and standard plates if you have standard pieces in your shop. There's basically settings for controlling everything. Okay. When you're satisfied with how your model's built, you click this button right here, Process and Create Shop Drawings, and with one click of the mouse, it's going to go through the model. It's going to figure out what frames to what. It's going to solve all those clashes, because that's what detailing is. And when it's done, it's going to produce the shop drawings in DWG format. Simple AutoCAD DWG files. So you can actually take those DWG files and work on them outside the system or outside the model. So if you have 10 people in your office, 1 or 2 of them can have the system building models, and you can have a couple other people scrubbing up the drawings, and you don't have to have licenses for all 10 people in your office to be effective. When it's done, it produces the reports that you can print right from here, or you can print it later on from Notepad or Microsoft Word. Okay, you can see that it produced a 3D model. We're looking flat down on the building, straight down. First thing I want to do is show you some shop drawings. So let's take a look at sheet 3A. If I click this icon here, which we call the termite, it'll actually open up shop drawing number 3. Now this drawing number 3, you can see the title blocks all filled out, bill of materials all filled out, all weights are extended, all combinations are made. Now our shop drawings are very clean because the only thing we show you is what the shop needs and what the checker needs. We didn't forget about the checker. All our plates and angles and connection material are drawn up front on what we call CM sheets or correlation sheets. We invented these back in 1973 and everybody copied us. All like angles are combined in a project standard mark and are standardized throughout the project. If you have standard shop marks, we'll use them. All you have to do is define them in the system and it never forgets them. So here's angle A1, there's 12 of them total. And this is where you fabricate the angles and the plates from. Okay, here's the base plate that I put in for our moment columns. Here's the one for the tube column. Here's some shear plates. Everything you need to make and check these plates are on these sheets. The bill of materials all filled out for you. And by the way, we support metric now as well. So you can input the job in either imperial or metric and produce the drawings in either imperial or metric. So if it was done in metric, this would all be in millimeters and the weight would become mass. Okay, let's exit that. Let's go back to our shop drawing 3A. Now since the plates are pre-drawn on the CM sheets, we don't have to show you all those dimensions again. All we have to do is locate it for you, make sure you don't put the plate on backwards by giving you that dimension, show you how to weld it or bolt it, and give you the piece mark, and cut a section if it's necessary. Now this is a raw drawing right out of the system, so there will be a little bit of cosmetic overlapping, but compared to other systems, these drawings are exceptionally clean. This little round thing with the X in it's the target mark, so they know in the field which side the strike face is. They put a little X or a strike mark on the plate in the shop. There's your offset for checking. There's your grid line location. There's what the information the checker needs, and the extension dimension is what the shop needs. Now if you take a look at the web section here, remember we had a non-moment connection going into the web with the SPI connection, which was a shear plate with a continuity with a stiffener plate top and bottom. Going into the flange, we had a moment connection with continuity plates and doubler plates. In any other system, that would have been a clash, and it would have shown you that in 3D, which means you'd have to go through every single joint in the system that had that issue and write a special macro or connection to resolve it. That is time-consuming and error-prone because you could miss it. Our system is a detailing system. It's not interested in showing you clashes on the screen. It's interested in fixing the situation and producing the shop drawing and calling it a day. So what the system did in this particular situation is it got rid of got rid of the half-inch stabilizer plate, because the continuity plate is much more important because it transfers the moment through the moment frame. Since we eliminated that half-inch stabilizer plate, the system automatically took the shear plate and extended it up and welded it and put a little clip on the corner to clear the fillet weld and welds it underneath the continuity plate. You didn't have to think about that. It was automatic. Now, this connection was written with the web, but these doubler plates were written with the moment flange connection. These were different connections, yet the system was smart enough to resolve the clashes or conflicts between the connections. It saw the thickness of the doubler plate, and it automatically set it back to miss that. No other system does this automatically. None. Every dimension that you need for checking and for fabrication is here, and nothing extra. The only scrubbing you got to do is cosmetic. All the sections are cut, the flip-up views are shown. Notice how the system is smart enough not to extend the doubler plate through the cap plate. It stopped it and welded it underneath. Bill of materials automatically filled out. Weights are extended and the title blocks filled out. Let's go to the second floor. Okay, take a look at those clip angles. Look at what the system did with that 3-inch offset. That was automatic. You didn't have to, all you had to do was define the steel and write the global connection, or in this case a drag and drop connection, and you were done. So let's take a look at this beam 1631. That's piece mark 15C. So we click on it. And there's the 3-inch difference between the beams. There's the extension dimensions for the checker. Extension dimensions are for the shop, the out-to-outer for the checker. The bolts are listed on the end of the material. There's a little scrubbing you got to do. Okay. There's the point-to-point, the minus dimensions, which gives you your final length, which will be the same length you find in the bill of material. And notice, unlike a modeling system will take a 3-dimensional piece and scale it down to fit on the sheet of paper. That's not the way or the standards that we were taught to draw by hand. And our system, since it's a detailing system first, follows the hand drawing conventions that we used to draw by hand. That allows us to put 6 beams on a sheet, draw the sections down the middle. Now we only have 5 in the sheet because we needed the extra space because we had extra sections. We also have the option of doing 1 sketch per sheet, 11 by 17. So taking a closer look, here's a section that was automatically cut. Again, we don't have to show all the physical dimensions because plate P11 was shown completely detailed out on the correlation sheets. Okay. Let's look at a moment beam. 11A. There you can see the preps. Notice that the system cut the web back a 1/2 inch. That's again another clash. The fillet weld was 5/16 because it was a 1/2 inch thick shear plate for the moment connection. On a moment beam, there's only a 3/8 setback. Therefore, the beam only clears the weld by a 1/16, and there's no guarantee that the weld's going to be perfect in the field. It's probably not. It's not rocket science. It's structural steel. So the system knows that and cuts the web back a 1/2 inch so that there's never any conflict with the weld, which is exactly what I would have done by hand. The elevations shown on the beam, everything you need to know is here for the shop and for the checker. Okay, let's make an erection drawing. So I can pick a point going from here to here. And we're going to go from the second minus to the second plus, second, give it a friendly name. We'll make it a mark plan. Quarter-inch scale, you can draw it in any scale you want. If you fill in UL here, it'll actually show you all the reactions of the steel. So we're going to make a mark plan. Okay, and run. And here's our plan with all the dimensions shown. This is the finished product of your erection drawing. And we can also show it with field bolts. Go back to plans, edit, and make it a field bolt plan. Apply, okay, and run. And now what it's going to do is show the beams with the field bolts on. At the top is the left side and the bottom is the right side. So we do the field bolts in report form. We show them on the shop drawings, in the bill of material, and of course we show them on the erection drawings. So now if I go to material, show members as lines, uncheck it. It's now going to show it as a 3D profile. So I can go to the navigator and look at a front view. And I can see, notice we show the holes in both the plate and the beam. You should be able to see daylight through there, because obviously if you can't see daylight, it's not going to fit. You're always going to see daylight in our system because it's impossible for it not to fit. If you build a model and write a global connection, everything we produce is going to fit. You may not have input it right, but it will fit. Okay, and of course now you can also take the view and go to Visual Styles and shade it in, and it'll show it as a 3D model that you can then flip around and rotate around on the screen, which I know is a lot of fun and is very, very impressive, but that's not what we get paid to do. We get paid to produce shop drawings, and that's what I concentrate on because I'm a detailer. Show members as lines. Okay, so let's go back to a plan view. Okay, I'm going to go to my computer, and I'm going to go to my C drive, and I'm going to go to AutoCAD drawings, and this job was called Core 2. This is where all the DWG files are, so you could take them and put them on another machine and work on them separate. Okay, if you go to SoftSteel, Jobs, this is where your job data is. There'll be a folder in here called Core 2. If you go to Drill and go down to Core 2, here's all the CNC files. So we can go to 11A, and there's the DSTV file for beam 11A. Here's the header record, the profile, the holes, and we did powder marks, which are lift marks for the center of gravity, which I automatically turn on. And then depending on your needs, we can turn on layout marks or powder marks for the plates, for the copes, for anything you want to do layout work with. I typically just like to punch the holes and do the lift marks. We also do petamat files. If you have petting house equipment, most of the new petting house equipment now uses DSTV files, but if you're using one that uses petamat, we support that as well. We also put out the plasma files for the plate, and you can export the model as well. I tried to keep this demo to an hour, and we're right at 1 hour. So this is the end of the demo. I appreciate you taking the time to look at our system. With detail, what we're all about is producing high-quality shop drawings with a minimal amount of effort. Our learning curve is typically just 3 or 4 days, not months or years, like some of the modeling systems. It's an automated 3D detailing system that produces a model with minimal amount of effort, with high-quality shop drawings and CNC files. A lot of the buildings in Las Vegas were built with this system that did the detailing, including the city center. The hotel towers were detailed on this, as well as a lot of the other buildings in Vegas, LA, New York, all throughout the US. I personally use this system every day in my detailing office. It's the perfect system for structural and industrial type detailing. If you'd like more information, please contact SoftSteel, or in the Middle East, Africa, India, and Asia, please contact Core Dynamics, and we'll be happy to give you further information, pricing, or give you a further demonstration of the system. Thank you very, very much for your time, and you have a wonderful day.